We now continue with chapter 5, which is AI-based robust communication and computing. As you know, the convergence of communication and computation, along with the integration of machine learning and artificial intelligence, stand as key and empowering pillars for the sixth generation of communication systems, 6G. So now here we see a small list of related works related to this current chapter. So dealing with channel uncertainties, using model-based approaches, but also using deep learning methods to address uncertainties. In this chapter, we consider joint communication and computation system as illustrated here. So we have a single base station equipped with L antennas and embedded computing ability serving K single antenna users. That means we have an edge computing based architecture which is supposed to support computation hungry devices in the network. So in fact, in many 6G key applications like image and video processing or digital twinning, the devices depend on strong remote processing capabilities at the network edge. That means we need to have an embedded edge server at the base station. Alternatively, it could be an uncrewed aerial vehicle, in high altitude platform station, etc. In addition to the computation capabilities, we need also to have communication capabilities such as device association, beamforming, and power control. Now, in such cases, each of those devices experience a delay consisting of two parts, namely the communication delay, that means the time loss on the physical communication medium, and the computation delay, that means the time for computing the tasks of the single antenna devices. In analyzing the impact of uncertainties, we need to introduce some new variables here. So first of all, the network setup is as follows. We have a downlink system, so in particular a downlink mobile edge computing network with one processor, one base station, and K devices. And what we do is we model the channels and the computation requirements, so given as H, I, K, and W, K respectively, statistically. And we assume that there's an estimation error with respect to the channel and the computing requirements given by H, I, K, R, and W, K, R, which is unknown to us. So now we have to consider this setup by taking into account the resources we have to manage. That's the transmit power given by PKTX for user K, which is then collected in a vector given by PTX. We have the computing power PCO, and we have the computation allocation cycles for each user Fk, Co, which is then collected in a vector FCO. More details are available in this paper here, which was recently accepted at the ISWCS in 2024. Here we consider the coupling of communication and computing or computation power consumption at the base station, which leads to the overall power constraint given here with the total power budget Pmax. So this expression emphasizes the intervened communication and computation powers, especially underlying the need for careful selection of the joint resource allocation under limited resources. So in addition to this, we have a computation capacity constraint, which is given here. So the sum of all allocated computation cycles should be upper bounded by Fmax. And we have the communication data rate given by this expression here for each individual user. Now let's have a closer look at the uncertainty model and delay we are going to use in this tutorial. Certainly the channel uncertainty is going to have an impact on the objectives. So how do we model this? In practice, the channel uncertainty distribution is not known. Yet, as channel estimations can be sampled in large amounts, a data-driven approach is able to learn the channel uncertainty implicitly. Certainly, also the computation uncertainty has an impact on the objective. So how to model this? First of all, the computation requirements given here by WK may not be perfectly known at the base station, as only an estimation WK is available. More specifically, computing environments are highly dynamic. That means they vary depending on system load and concurrent processes, and system dependency. That means the interrelation of input data characteristic. So there are various statistical models for WK in the literature, including uniform, normal, and gamma distributions. So in this tutorial, we address computation uncertainty again using a data-driven fashion, where we sample large amounts of uncertainty realizations and train the DNN accordingly. So by further considering the communication delay discussed earlier, devices experience a total delay TK consisting of computation and communication delay. So in order to achieve fairness among all the K users, this tutorial basically aims at minimizing the worst case delay TK max among all devices. Yeah. Computed via the ground truth channels, that means HK, and computation intensities WK. Now let's look into the details of robust delay minimization. Again, we have two uncertain problem parameters, which is the imperfect channel knowledge. That means we only have the estimation of the channel given by HK, and we have only an approximated computation requirements given by WK. Now, what is the benefit of utilizing or proceeding with robust optimization? So this is nicely illustrated in this plot, which we borrowed from this paper here from 2013. So what we have here is the objective characteristic as a function of the control with the impact of the noise factor. Now, if we don't perform a robust optimization, we might end up basically by arriving at this nominal optimal solution. But then, taking into account there's going to be a variation due to the noise factor, we might end up having this solution, or even worse, we might have this solution. And you see that the variation basically in the objective is quite high. Now, instead, if you proceed with a robust optimization, then we might end up in having this solution here, and if the variation due to the noise factor kicks in, then the difference to the robust optimal solution can be either here or here. And you see basically that the impact due to the variation in the objective characters is low compared to the previous case. Even more, you see that the objective which we have obtained from the robust optimal solution might be higher than the final or the overall performance which we have when we don't perform robust optimization. So now, taking this into account and considering our robust delay minimization, where basically this curve is inverted because we are performing minimization, we have this situation that the unknown distribution of the worst case delay Tmax is given, and the basic idea of uncertainty injection is now to estimate the statistical objective numerically, and we do this by using a large number of realizations or samples of the uncertainty. Afterwards, such realizations are then injected after the DNN output to compute a large number of objective values, and then these objectives are then used to obtain an empirical estimate of the robust objective. And such estimates is then used to derive gradients and update the DNN parameters via backpropagation. Technically speaking, the robust delay minimization can be formulated as an optimization problem as shown here. So we have a minimization problem where we minimize this objective T max parameterized by gamma, subject to the constraints mentioned here. Some are due to computation, some are due to communication, and we have to achieve this by utilizing the resources available to us in the best possible fashion. So the first constraint is making sure that the probability that Tmax exceeds this objective are lower or equal to gamma. Then we have to incorporate the models we are assuming. So we are looking at the worst case delay among all the users. Then we have some constraints with respect to the computation, and we have some constraints regarding the power available to us in the network. As mentioned before, we are using a data-driven approach here to solve the optimization problem. So we have a deep learning framework which utilizes a deep neural network, a DNN, and this DNN has as input the channel estimation and the computing estimation, and as output the power and the computation allocation. As shown on the previous slide, the adopted objective is also a function of the worst case delay. Therefore, what we do in the training phase is we sample n realizations of the channel and computing uncertainties given by HR and WR as shown here. And with the values of those delays derived from those uncertainty samples in the previous step, we sort all the m delays and select the gamma times m's highest value, which essentially forms an empirical estimate of the gamma's quantile worst case delay T max parameterized by gamma, which we also refer as T hat max parameterized by gamma. And then we basically perform backpropagation to update the parameters of the neural networks. Now let's have a closer look at the results. So for the simulations, we assume to have 8 antennas available at the base station. We have 6 devices, each with a single antenna. For the computation requirement, we assume the distribution following a gamma distribution, and the channels follow a Gaussian distribution. For the power, we assume to have 38 dBm available, and we have a system which supports 1 megahertz of bandwidth. For the DNN, we assume that we have 10 fully connected layers and 400 neurons per layer, which apply the ReLU activation. Now, in addition to the proposed joint uncertainty injection scheme, we have 3 benchmarks. The first one is a modification of our scheme, which is referred to as COM-UI, which only accounts for communication channel uncertainty. The second one is referred to as COMP-UI, which is a method only taking into account the uncertainty in the computing requirements. We also compare performance with respect to a regular DNN, that is a scheme that does not account for the uncertainties at all and is trained according to the estimated inputs only. Now what we have here is a particular plot showing the robust delay T hat max parameterized by gamma as a function of the channel estimation errors. Note that here for the setup we assumed the fixed computation estimation error for W. And now what we see is that all the uncertainty injection schemes demonstrate improvements over the baseline regular DNN with gains ranging from 8 milliseconds to 20 milliseconds. Nevertheless, basically our joint uncertainty injection scheme consistently achieve the lowest robust delay across all levels of channel uncertainty variances. And this essentially highlights the generalizability and the flexibility of joint uncertainty injection in different uncertainty scenarios. So the next plot as shown here reaffirms essentially the advantages of joint UI by again showing the robust delay, but now as a function of the computation estimation error variance given by sigma w squared. And in particular for very high errors, basically we get more insights when we compare the slope of the regular DNN with and also the communication uncertainty method and compare this to the joint uncertainty method and the computation uncertainty method. We see basically a relatively small increase in performance degradation in response to high computation uncertainties. So, and we essentially see that basically this joint uncertainty approach provides a lower delay in face of increasing uncertainty and generalizes both the comp UI and the com UI. Now let's summarize the benefits of the proposed scheme and the challenges and limitations of it. First of all, the AI-aided robust communication and computing provides minimized worst-case delays for network devices, and it was general enough to account for different parameter realizations alongside real-time inference during operation. So far, we have only realized it in a centralized manner, and that means it's not really scalable. So when we look at the resilience, basically, of those DNN-based and uncertainty injection approaches, we see that we can provide reliable service in face of uncertain channels and computing requirements, and we have been able to increase the robustness with respect to estimation errors. That was the last slide of chapter 5, which addressed AI-based robust computation and communication approaches. Now we have again the opportunity to take your questions and provide the answers. Are there any questions?